So let's just do an aside and talk about wave interference. I'm quite sure you must have seen this elsewhere. We must have talked about it a little bit in 115, 116. I'm not sure. But in any case, I will take this as a review. Let's just say that you have a wave. It can be a water wave, it can be a sound wave, it can be a light wave, doesn't matter what kind of wave. If I have a wave, right, a wave has this property that it has crests and troughs, right? Crests and troughs. And you can think of that as the wave is something which would be at equilibrium, that's the dotted line, and the equilibrium, and so some measurement of the wave, whether it's the displacement from equilibrium or whatever, goes above and below equilibrium, above and below the x-axis. But that's the equilibrium axis, right? So it gets positive and it gets negative, and it gets positive and it gets negative, and it gets positive and it gets negative. Whether this is, current in an AC circuit or the pressure in a sound wave, it goes back and forth, etc. Okay, so let's take two waves and ask what happens when two waves overlap, right? So let's take a second wave. Let's just, for the sake of making this an easier discussion, make it the same wavelength, same frequency wave. But, I guess if it was light, I was going to say one is blue light and one is green light, but that wouldn't be the same frequency and wavelength. Okay, so it's just two waves, and let's say this is two sound waves, and those two sound waves overlap. So now think of this as maybe two speakers in a stereo system, right? So there's sound coming out of one speaker and sound coming out of the other speaker. That was meant to be that. I don't know what those pictures were, but they were meant to be speakers with sound coming out of them. Okay, so if you are listening to that sound and you are at a point that those two waves overlap, what happens when two waves overlap? Well, when two waves overlap, they undergo a process called interference, or they interfere, right? So two waves that overlap interfere. Well, what does that mean? There's nothing special about it. It's really just that they add. Two waves, or more, but two waves that... So there's nothing surprising there, right? Two sounds that you hear at the same time might sound louder. But that is what's special, is that this is a special kind of addition. They add only in a special way, right? They add if their two peaks are at the same place as their troughs. Then it's gonna sound louder. But if I shift one of these waves so that a peak is at a trough, then it's going to sound quieter, right? So you've heard these terms before of constructive and destructive interference. You get constructive interference when a peak overlaps with a peak. You get destructive interference when a trough overlaps with a peak. You get anything in between when you have anything in between. So let's do this a little bit more carefully. Let's say that I have the blue wave and the green wave, and they're two sound waves that are reaching your ear at the same time, and they reach your ear so that a peak of one reaches your ear at the same time as the peak of the other. So, this could be your ear over here to the right. I don't know how to draw an ear. Right, there you go. It's like an eye, but it's an ear. All right. In any case, this could be light coming to your eye as well. But in any case, what happens is that if the blue wave and the green wave each have an amplitude of A, then they're going to add to be the black wave, which has an amplitude of 2A. That's called constructive interference. The peaks and troughs add. As opposed to destructive interference, if the waves are offset so that when they arrive at your ear or your eye or whatever's detecting them, then such that one peak is where the other trough is, then what's going to happen is the positive amplitude and the negative amplitude are going to add, but plus a minus is equal to 0. And so what's going to happen is that your sum is going to be a flat black line. You're not going to hear or see anything. It's called destructive interference. This is a well-understood phenomenon. We can demonstrate it in the classroom, and you can do it with sound. You can do it with any kind of wave. And you've seen interference patterns on water. You've seen interference patterns on light. You've even heard interference patterns, though you may not realize it. One of the things about interference patterns in sound is this concept of a dead spot in a concert hall. There are places in a concert hall where the sound just is not as loud as other places, and that's because it's because of the shape of the hull and the way the sound waves work, that the waves more preferably destructively interfere at that point. Now, you got to be careful, because in this example that we have in front of us, we're talking about a single frequency wave. But when you're talking about a concert hall, you've got all kinds of frequencies. So while there's always going to be some constructive interference and some destructive interference, there's so many different kinds of waves adding at one time that you're never going to usually get a lot of destructive interference, and you're never going to get completely destructive interference. You can only get completely destructive interference when you've got two or more of the same frequency wave that come exactly a half a wavelength apart. What do I mean by a half a wavelength apart? How do you get these two waves to be where a peak is, a trough is where a peak is? Right, so let's just take our original picture of the green wave and the blue wave. So here's the blue wave, and here's the green wave. And these two would constructively interfere. But if I slow down one wave, or if I take the source and I move it backwards, which is the same thing as slowing it down, I can either slow it down or move the source backwards. I can just shift that wave backwards so that I am just moving it backwards so that we get that. Right? We can do that literally by taking the speaker that's playing the wave, and we can just shift it backwards. Right? Or we can do something to the wave. We can have the wave go through some container filled with a gas which has a different speed of sound. And so we have slowed down the sound by some amount, and we've shifted the sound relative to the blue wave. So you can shift it, again, in two ways. You can either simply shift the source backwards, or you can slow down the wave for some amount of time in order to shift them relative to each other. So that's how we shift it. Now, when do you get completely constructive interference? You get completely constructive interference, completely additive interference, when a peak is lined up with a peak and a trough is lined up with a trough. That is when you receive the waves at the same time. Let's say that this is the front of the wave. Or I could shift the wave back, not by half a wavelength, but by a full wavelength. If I shift the wave back by a full wavelength, pausing here because I realize I'm hoping you know what these terms mean, right? A wavelength is the distance over which a wave repeats itself. So that's a wavelength, distance over which a wave repeats itself. So a full wavelength, the distance over which a wave repeats itself, is that distance there. So that is a wavelength. So if I take that green wave and I shift it back by a full wavelength, so I'm going to have it start here. Whoops. Oh well, that was a little messy. I didn't draw it quite to scale. Okay, I redrew that just to try to show. In this case, I had the blue wave on top and the green wave below it. But instead, what I'm showing is that I have shifted the green wave back by one full wavelength, right? One full wavelength. If I shift it back by one full wavelength, then the green wave, the new green wave, is still lined up with the blue wave, and we will still get constructive interference. So how do I get destructive interference? So I get destructive interference by taking the green wave and simply shifting it back a half a wavelength. If I shift it back a half a wavelength, I have now shifted it so that its peak is where the blue wave's trough is, and its trough is where the blue wave's peak is, right? So I get constructive interference if I shift one wave relative to another by a full wavelength, and I get destructive interference if I shift one wave relative to the other by a half wavelength. We repeat that. So I get constructive interference if the waves arrive at the same time, or shift relative to each other by a change in distance, right? We've moved one wave by some delta D, some change in distance, which we've done by either moving the source or slowing it down or speeding it up at some point. And so that change in distance is going to be plus or minus a wavelength, or 2 wavelengths, or 3 wavelengths, or 4 wavelengths, etc., right? Or n lambda. So if we shift one relative to the other by n lambda, we get constructive interference. Whereas destructive interference is if we shift the wave relative to each other, whether it's forwards or backwards. I'm just going to draw it in the backwards direction here. Delta D equals, right, for example, lambda over 2. We can shift it forwards by delta D is lambda over 2. Or we can do it not 2 lambda over 2, because 2 lambda over 2 is a full lambda, but an odd number of lambdas over 2, right? 3 lambda over 2 is 1 wavelength plus another half. 5 wavelengths over 2. So, or 3 lambda over 2, 5 lambda over 2, plus or minus in either direction, right? So it's going to be, or in general, it's just any odd number of half wavelengths, right? 3, 5, 7, etc. Any odd number of half wavelengths. If it's anything in between, an odd number of half wavelengths or an even number of half wavelengths, notice that this is also just an even number of half wavelengths, then it's going to be something between constructive and destructive interference. Let me just show you some examples of interference. So this is a good example of water wave interference. In this case, we've got 2 circular water waves being created by tapping the water, right? So somebody's, whoops, I did not, okay, sorry. This is an example of water wave interference where somebody is tapping the water here and tapping the water here, and both are creating circular wave patterns that go out. But you can see that there are these lines where there is no disturbance. These lines indicate, if you look carefully, right, there's no disturbance, right? The disturbance are these things, which are traveling outwards. That's the disturbance. Those are circular arcs, which are traveling outwards, circular arcs traveling outwards. But there are lines where there is no disturbance. Those are the areas of destructive interference. So you can assume that anywhere along those lines, if we take any point along these 2 lines, let's say, for example, this point right here, and we look at the source, the wave coming, oops, let me draw this differently. So I just drew a ray, a black line, showing that the wave from the source on the left had to follow the black line from the source on the left, and a wave from the source on the right had to follow the black line to the green point, and I'm just looking at that point where there is destructive interference and say, oh, well, so the length of those 2 black lines must be different by either 1/2 a wavelength, 2/2 a wavelength, I'm sorry, not 2, 1/2 a wavelength, 3/2 a wavelength, 5/2 a wavelength, 7/2 a wavelength, etc. And that's going to be true for any point on any of these destructive interference lines. Now, the constructive interference lines, it's a little harder to tell, but we can probably assume that we have perfectly constructive interference exactly halfway between them. Let me change the color. Okay, so we probably have constructive interference going right along here, and we can say, well, let's look at any point along there. So let's look at this point. We say, the ray coming from the left source and the ray coming from the right source, those are coming equidistant. Or they're 1 wavelength apart, 2 wavelengths apart, or 3 wavelengths apart. In this case, they're clearly equidistant, so they're 0 wavelengths apart, and we got constructive interference. If we look at another point of perfectly constructive interference, which let's assume is this one here, then again, if we take the distance from one source and the distance from the other source, then one of those sources is going to be 1 wavelength farther than the other source. And in this case, I actually do know it's 1 wavelength farther. You can see if you can figure out why I know that. Why one source must be 1 wavelength farther than the other source. And by wavelength, we mean the length of the wave in the water, right? The wavelength of the water is this right here. Whoops. Because the distance between any 2 of these peaks, right? It's the distance over which the wave repeats itself. So we can measure the wavelength, and then we could measure those black lines, and we could tell that they're 0 wavelength. Anyway, we could figure out where we have constructive and destructive interference. So we can see that. You've probably seen pictures like this before somewhere, but this is light interference projected onto a screen. This is light coming through 2 slits, right? So the last example was water coming from 2 sources. So this is like light coming from 2 sources, but you can actually just take a laser and shine it through 2 slits that are really close together, so the light goes through both slits, And then you project that on a screen, and on the screen you get an interference pattern, because now you've got basically the two slits cause two sources. By two slits, I literally mean take like a piece of cardboard and take a razor blade and cut two holes in it. I'm just showing it in 2 dimension, or in 1 dimension, the bottom of the screen. And then take your green laser and just shine it through those 2 holes. And what happens is not what I just drew. What happens is when the laser gets to those 2 slits, the 2 slits break it up and make it act like it's 2 sources of light. Right? So we've got 2 sources of light. But the light coming out of each of those slits is going in all directions. So a slit acts like a single point source of light. Don't know if that was very obvious. Let me redraw that real quick. A single slit will act like a single point source of light. So that's one of the slits, and then the other slit is going to have the same kind of pattern, and it acts like the water. You're going to get constructive and destructive interference. That just sort of looks like an alien worm or something. But on the screen, you're going to get constructive and destructive interference points, where you know that wherever there's a bright point, the 2 light beams must have traveled the same distance, or a difference in distance of 1 wavelength, 2 wavelength, 3 wavelengths. And wherever there's a dark point on the screen, then the beam, you can measure the distance back to the beams, and the distance back to the beam is going to differ by an odd number of half wavelengths. 1 half lambda, 3 halves lambda, 5 halves lambda, 7 halves lambda. Now, what I want you to recognize here, this is super important, is that this diffraction, this is what's called the interference pattern, not diffraction pattern. Well, it is. It's related to a diffraction pattern, but the interference pattern we see on the screen, this is a measurable pattern. Like the distance between these slits is millimeters. I've blown it up for you on the screen here. But the scale might be something like what I've drawn here. 1 millimeter is sort of the distance between 2 slits, what I've drawn on the top of the screen. Yet the wavelength of the light, I don't know if you're aware, but the wavelength of light of electromagnetic waves is incredibly small, right? It's immeasurably small. When I say immeasurably, I mean directly immeasurably small. The wavelength of the light itself is of green light. Let's say in this case we do have green light. I won't bother changing the color to green. But the wavelength of the light is about 500 nanometers, or 500 or 5 times 10 to the minus 7th meters. So the wavelength is very small and would be hard to measure, but the interference pattern is quite large and is easy to measure. So you can use the geometry of interference patterns to measure very small changes in distance. This is the key to interferometry. Because wavelengths are very small, and the distance from a dark spot to a light spot on your interference pattern has to do with a change in the path length of half a wavelength, then we can use interference patterns to measure very small changes in distance. So measuring a millimeter on an interference pattern might equilibrate to your source being a tenth of a micron farther than another source.